All right. So let's get back to. So I hope you had some rest over the weekend. It was a longer weekend, and I hope if you traveled that you didn't have a lot of trouble. I did get a number of emails with some travel issues, which motivated me to say, okay, so 5 o'clock today is okay for submitting your homework. If you need that extension. If you don't need it, you're done with it, you're done with it, you give your homework. So this is just for, to make it easier on those who did have some travel issues. All right, that's first comment, and the second comment is that I did upload the new Lecture7. So you can download it because we actually probably need some of it today. So last time on Monday, if this free holiday is still somewhere on your brain, I hope, that didn't get completely erased in a week, we have started a topic about curve-fitting. So can anybody recall what was this curve-fitting about? Why would I want curve-fitting? So I have some examples of data. Let's look at this data of permeability versus porosity. Everybody remembers what permeability is? Stability of porous medium measures, ability of porous medium to transmit fluids. And porosity is simply void content. So those are some of the two most important petrophysical properties that we're going after in petroleum engineering. So permeability is not always a simple function of porosity, or rather almost never, in any reservoirs that matter. So we often want to have some sort of relationships. We would like to have a functional relationship based on possibly some simple measurements. Porosity is simple to measure. Permeability, not so much. So to measure permeability, there is no way to do bell logging measure of permeability without really stopping the entire operations and being rather expensive. But porosity we do have. We have neutron porosity, for instance, as a bell log. So I would like to be able to compute permeability based on the porosity that I get from my bell log. But that's not always possible. So there is a range of petrophysical relationships. But I could simply also do, if I do have the time, I could take a lot of samples, measure their permeability, and then get data. So one such data is shown here. We have a range of sandstones in porosities from very rather tight, 5% or so, to over 25%. Right? If I don't have the relationship, if I just have the data, it's extremely hard for me to use that information somewhere else beyond just plotting this block. I would like to have a function. Permeability is some coefficient times porosity plus a function of porosity. And it's this task of curve fitting to actually come up with that function. Now we do have to know what do we want to fit. So I could always just strike a line. Line would not do really well here, right? Because I have sort of a curve. But this curve that says model, that is actually a model that has some coefficients to it, 1 or 2. We can then try to estimate those coefficients based on the data. And that's the task of curve fitting. After that, I will actually have a functional relationship that I can use somewhere else. So I can possibly use it in some other reservoir to predict what the permeability is based on porosity. So that is the task of curve fitting. The key thing is look at the data. You have to come up with the function you want to fit your data with to begin with. Okay? So looking at the data is pretty important. Doing things blindly is not necessarily going to work. Okay, so the simplest thing that I could ever do is to fit a linear regression and a linear model. And that linear model simply says, okay, my y component of the data is some coefficient a, I'm calling it a0 plus a1 times x component of the data. If I have pairs x and y, that should be simple enough. And then I have some error, and I'm trying to minimize that error. We have gone into a long story last time. What type of error do we minimize? And what turns out to be the best is to take the difference between my y, the data point, right here, and the actual model prediction right here, and square it. And then take some of those, we call those squares of residuals. Okay, so those are my residuals, these differences, and their squares are, when I sum them up, sum of the squares of the residuals. And then I'm trying to minimize that. And the reason that works, okay, so this is my sum of the measured data minus whatever model gives me. In the linear case, this is the model, okay? So this is the sum that I'm trying to minimize. Now the way minimization works, I have two coefficients I'm looking for. In this sum, what I don't know is a0 and a1. I know x1, x2, x3, x4, and so forth. I know y1, y2, y3, and so forth. I have the data. I might have a lot of data, but I have it. Okay? So all these xi's, yi's are known. So if I want to find what is the best fit to this SR, it's to minimize this function SR, which is a function of two variables. I need to make, normally if I wanted to minimize f of x, I would look at f prime of x being 0, right? Here I do partial derivative with respect to a0 and a1. So I'm basically making all of the partial derivatives 0 instead of just one derivative. So this is the difference between single variable calculus versus multiple variable calculus. And I know multiple variable calculus is your favorite, multivariate, right? Your favorite topic, no? So, well, it's difficult, but it's very useful. So here, when I take partial derivatives with respect to a0 and a1 of that sum SR, I will get these expressions. And when I clean them up a little, just like in anything, I put my unknowns a0, a1, and anything that multiplies them on the left, everything that I know on the right, and I get myself a system of equations. Not only that, this is a linear system of equations. We know everything that there is to know by now. So I have n, this is simply number of data points, times a0 plus sum of xi's, a1, is equal to sum of yi's. Yes? And then I have sum of xi's, a0, sum of xi squared, a1, is equal to sum of xi, yi. Do we know how to compute sums? We've learned that, right? So if I give you two arrays, x and y, you know how to compute all of these sums? I need 1, 2, 3, this is the same, 4 different sums. Yes? They're actually relatively simple compared to what we had on exam 1. Okay? So I compute these 4 sums, and then I have a 2 by 2 system. Now 2 by 2 systems are simple. I can go and use a solver. I can set up a system and use a solver. But 2 by 2, we actually have formulas. Do you remember that you got the formula somewhere in whatever math class you had? With determinants and whatnot for 2 by 2 systems, you can actually have a formula solving it. And we can write down that formula. If you have a formula, we should use it. So basically, when you have the systems, what solves a0 is this, and a1 is this. You now know what comes next, right? You're going to get an exercise. And I'm going to share a template, so I'm going to give you this data already. And I want you to create linear regression function that will take this xy vectors as input and provide linear fit a0, a1 as output. So let me just quickly share it. I don't think I uploaded it.
this is it. Save. Files go. So open up your Python Anaconda if it hasn't been open for a while, or if you restarted it. So I'm gonna upload the notebook linear regression template. So here I have a bunch of points, and we're gonna simply try to fit a line through them. Whether that's a good idea or not, we're gonna see in a moment whether it is. So have you downloaded the template? Open it up. If you open it up, the first cell has just data. So the data that was on the slide is just typed in. And then the first cell is just plotting the data. Okay. So you should get, when you execute the first cell, you should get something like this. Is everybody there? Now let's just first look at the data. If I attempt to strike a straight line through these data points, is that a good model? No. We're going to do it anyway, because that's the simplest. And then we're going to improve. Okay? So if you just, however you do the data, straight line here, straight line here, straight line there, like, there are some better lines than the others, but it's not a very good model. But let's do it anyway, because that's the simplest model we can do. So below this, you have sort of a template for a function for simple linear regression that takes x and y as an input, just like the x and y given above. And I already kind of typed in some of the things. So n is length of one of these vectors. And I kind of gave suggestions for the naming the variables. Sum x, y, sum x, sum y, sum x2, which is sum of x squares. So I want you to compute these sums. So I need, this is my sum of xi, yi, which is what I call sum xy. This is sum of x's, sum of y's, sum of x squares. And you basically need to calculate a0 and a1 and return them. At the bottom of the function, there is something called R2. Ignore that for right now. So basically finish up. And you can do sums the way we did them in class. You can also use np.sum. That will sum. That's just fine.
You need y squared too, or no?
I don't think so.
Oh, okay.
These four are needed. So you could use np.sum of x. Or you could set sum to 0 and then take a for loop and update all of these sums. However you want to do it, it's fine. I'm not testing you on how to do the sum. I figure we mastered that by now. What is this, by the way? If x and y are understood as vectors, what is this? Dot product. Dot product. If you remember the function for dot product of two vectors, you can use it.
Wait, what is sum x do?
I'm naming this sum x2. Because I already typed in R2, I'm going to explain what R2 is later. For now, ignore it. Oh. So have you figured out the dot product function? It is dot. Okay.
Oh, I see. Would it work to do a for loop?
Yeah,
Okay.
absolutely. There's something like 5 different ways to do this, whichever one you find good. This one is the shortest one to type, so I'm going to use them. But basically, alternative would be sum x, let's do one of these. Sum x is 0, and then for I in range of n, in range of n. This is the alternative. And you can, of course, then update every sum this way. Perfectly fine. So now the cell after that is basically plotting the comparison between the data and this linear regression. So this is how I run the function. Yes? Again, for now, ignore this output R2. And then I can plot the model and how it fits the data. So my model is actually this A0 plus A1 times X, whatever X is. That's what it means to be a linear model of X's, right? And I have just computed A0 and A1, hopefully. Moment of truth, if I didn't type in a problem. If I didn't, whoa, I typed in something. Some y square. Ah, that's in R2. Okay, so we do need y square for R2. My apologies. May as well add some y square. That's necessary for R2 that I'm keen on ignoring right now. Easy to add. There we go. You should get something like this. And not the best. Did you type in formulas correctly? Did you get something like this? I'm gonna wait for you to. Did everybody get this? No? Did you maybe flip A0 and A1? Yeah, there you go.
Oh no. Oh no.
So, what is a good fit? First thing, I would like to distinguish sort of how close am I to these points, right? So I would like some number that would tell me that in the case A, I'm doing better than in case B. In both cases, I'm plotting a trend through the data, however messy data is. Arguably, you can't fit this cloud here with anything really well. Okay, it's not really a function, but I would still like some number that tells me how well I'm doing. And that's this coefficient, which is often reported as R squared, that we actually computed at the bottom of that function. Okay? So there's two. I'm not going to go into the theory of why is this telling you, but basically it measures how far you are from the data. And if you actually pay attention to this R squared that you plotted in this case is 0.756. Okay? R squared 0.756 is not terrible. I wouldn't go below 0.6. Above 0.9 are really good fits, and 1 is perfect. Okay? So in these cases, whenever actually somebody shows you the data and shows you the linear fit to it, you probably want to ask what was your R2, and they should report R2 on the plot. Okay? Just so that somebody can. So this is not to say that because this was relatively poor fit 0.756, that you're not going to use it. If you don't have any other option, you will use it. Okay? And sometimes you do actually have a cloud of points that cannot be really well fit with any function because it's a cloud. It's not a line of any sort. But you still need that trend in the modeling you're using. And with the understanding that that's not a very good fit, you will proceed with using the trend anyway. But do be aware, like if you are doing the best you can, but that's not very good, but at least know that it's not very good. So always ask for R squared. So in this case, we want to improve. Okay? So another measure is, so R squared is much more common. Another one is standard error of the estimate, which takes that SR, those squares, and the sum of the square of residuals, and divides by n minus 2 because technically there's 2 degrees of freedom less than the number of data points. So that's why we are dividing by n minus 2. And that can be a measure too, though this one is much more common. Okay, so in summary, what we do is we take a model. In this case, we took a linear model. We took the measured data and the difference between the measured data and the model and took a square of that. And our model is trying to minimize the sum of residuals. Now, model has 2 coefficients, so we can do partial derivatives with respect to those 2 coefficients. And then that allows me to set up an equation. We end up with a system of linear equations. If I had a more complicated model, I would have 3 coefficients. I would get 3 equations. And I would set up, hopefully, a linear system based on the data. Now, my model could be highly nonlinear. And we're now going to next move on. So basically, I can then easily do a straight line fit, and this is what we just did. Now, if I actually have nonlinear relationships, I would, in taking those partial derivatives and whatnot, I would end up with a system of nonlinear equations, and those are not as easy to solve. However, there's a trick to linearize, and we're going to next show a couple of tricks how to linearize the relationships is essentially use that same linear regression function that we just did. So in some cases, I can transform my data that will basically, for instance, if I had something like this, which is a x squared relationship, power relationship, then a logarithm of it will be a linear plot. Okay? And that's the most common thing taken when modeling the data. Okay? I look at the data, I take the log of both sides, or at least one of them, and I will get a straight line. So how do we do that? Let's say that I have a relationship that is, let's focus on this one right here. Okay? So my y is some coefficient a2 times x to a power of b2. It's a power law relationship, one of the most common ones out there. If I take a log of both sides, doesn't matter which type of logarithm, then I'm going to have that log of y is equal to log of a2 plus b2 times log of x. Does everybody agree with me? And if you don't agree with me, can you take a piece of paper and actually go from there to that? So log of this entire thing is log of a2 plus log of x to the b2, and then that b2 can go down, right? So I will get this. There are two variables. If I define two new variables, my initial data is x and y. Those are my initial data. Can I define new data so that that new data is in a linear relationship? Based on my data x and y, which variants of those x and y's are related in a linear way? So log y and log x are actually related in a linear way. Log of a2 is some number. So I have that log y is some number plus another number times, and they're all constants. Everybody sees that? If I define myself y tilde as log y, I define myself a2 uppercase as log of a2. I define myself b2 is b2 and x tilde as log of x. Then I can rewrite that y tilde is a2 plus b2 times x tilde. That's a linear relationship between log of x's and log of y's. So if I asked you to do a power law fit to that data xy, where we saw that linear fit is not good, can you do that? Find me. So I'm going to assume, again, in curve fitting, we always assume that I have a power law relationship. Y is a2, some coefficient a2 times x to the b2. I'm looking for a2 and b2. That's what's not known. And then I linearize this relationship. Can you use that function linear regression that reportedly you all have now working? Can you use it to actually recover a2 and b2? There's some hints in your code. And it's gonna be a quiz grade.
So is A, the big A 0, is that log of little a2?
Mm-hmm. So how will you find a2? That's it.
So I'm confused that. What are we supposed to do? It's like I understand.
So I have data x and y.
Yeah.
I want you to find a2 and b2. using linear regression, you have code that for any data, it will return these coefficients for linear fit, right? That's the code. Any data, I'm calling it X and Y here. It could be anything. Think about it. Take a piece of paper to write this down, or think about it. As long as you, later when you're doing A2, B2, as long as you.
So you use LN.
Logarithm can be anyways, as long as you're consistent in the use of that
So
base.
A naught is out of log.
I don't know, I'm just following. I just read these. I just read the comments on there.
And then the rest of this is plotting comparison between the linear model and the power law model. And you should get something like this. So this was our original linear model, and this power law model does way better.
So do you use the same function as before?
Uh-huh.
It's just.
And then you have to recover what your A2 and B2 are. So here, if these two are linearly related, right? I can find these two numbers using linear regression. But then A2 and B2 are some functions of these coefficients that I get from linear regression, right?
Oh,
So that's why it's like compared to this.
So we know we can find big A0.
Using linear regression of log of the data. Right? Function doesn't care what you give it. So I could run linear regression of NP log of X and NP log of Y. Yes? And that will give me some coefficients. Now, how are those coefficients related to the ones that I'm actually looking for? That's the question. If you have more questions, I'm here. I can come in for a private consultation. Yes, so now from this case, you need to figure out and then your power model is here. It's actually one line, two lines. Oh, that's
It says here, right?
What? This, look. A0 equals
okay.
A1 equals B2.
Yeah. If you just compare these two formulas.
Yeah.
Then what do you do with you? Then you figure out. Yeah, because we have to make it. So we can do like e to the a0. E raised to the a0. Right? Yeah, first then. A is 0, right? Yeah.
Just compare the formulas.
Correct, yeah. Correct, yeah. And then
That's easy to easier. The graph. See, nonlinear is pretty much A0 is A1 on the
So right next to this one. No, rewriting.
yeah, big A. Oh, I guess because this only like this. And then you get, I'll just say this, and then all data in. I never did it. I did it. We did it earlier. Yeah, so basically we're doing that part by hand, but that's really just right here.
Right.
So no A1 is never bad.
Okay.
Big A1, not little A1. Wait, sorry.
Well, you know, error is the live power model.
So you get A0 minus they still don't equal each other because A0 doesn't equal log of A2.
You get it?
Yeah.
I think if I run it next, you just swap it. I think it should be like, it should be from, it should basically be like the graph, it's like a long column. It should be like to the like that one. It's not right. It's just like this. Okay. It's because you have to call the specific side.
I also got that.
It's a call. And then you have to make your X. So for our new linear regression, we have to change it to X. It's like 80 now. A2 is just right here, but that's right now. It just does the same thing we're doing.
Wait a second.
Have we figured it out?
I see. If it doesn't define these as these, you have to redefine them. I see.
A2 and
So power law relationships are the most common ones that basically this is an x squared that kind of straightens out when you take log. There's a number of different ones. You could do this. There could be variations of this, okay? And you can figure out what to, so it could be even like this. There could be a little bit of algebra here. And I have included on the slides a convenient table of different relationships that could show up. Okay. So this is the plot. You should get something like this as a plot. I just changed the colors a little. Yes? Yeah. Change it, yes. So when you compare that using A2 is the exponential function of So then you will create a quiz. I want you to submit the solved problem as a quiz. Okay. Now what else could we have? Pretty much anything. You have to look at the data and then you fit it. So it could be all kinds of polynomials. Obviously, in this case, straight line is not going to do a lot of good either. This looks parabolic. If it's parabolic, I could have three things I'm looking for. A0, A1, A2. The process is still the same. And yes, I could ask you to develop a process in final. Okay? Let's say, here's the model. Now, do linear, the best fit based on the least square, sum of the least squares of residuals, okay? Which is this. So this is my sum. And then I could have, I would set partial derivatives with respect to all of the coefficients to 0, work out the math. And in case of 3 coefficients fitting to parabolic equations, I would get something like this. So I would do all of these sums. They're a little tedious, but they're not complicated to compute. Right? And in this case, I would go all the way to xi 4. Okay? But this is a 3x3 system. Okay? We know how to solve a 3x3 system by now. So this would be a parabolic fit. I could also have so-called multiple linear regression in terms of 2 variables. Again, the process is the same. Question is, what is the functional relationship I'm fitting to and what are its coefficients? Okay? So I would again do sum of the squares of residuals and differentiate the sum with respect to every coefficient and set those partial derivatives to 0. So the process is sort of similar, and that leads to equations that I need to solve for the coefficients. So I just have to have in mind what is the functional relationship I'm fitting to. Okay? So this is what one would get for the multiple linear coefficients. So again, certain sums that I need to compute in terms of data, but other than that, it's a 3x3 system. Okay? All right. I see you on Wednesday.